Chapter 4, Section 7, Triangles and the Coordinate Proofs. When we're writing coordinate proofs, that means that we're going to be using the coordinate plane to help us to write proofs or to prove that triangles are congruent. This asks us to place a 3-unit by 5-unit rectangle in a coordinate plane. It's going to be important that you choose a placement that makes finding the distance easy. If we, for a 3-unit by 5-unit rectangle, it's not going to really matter that much. The distance isn't going to be that difficult to find. But we are going to be trying to use the distance formula some here. Like I said, with rectangles, probably not as big of a deal because you're not going to have any diagonal lines, hopefully. If you're placing it correctly, is what I mean by hopefully. But what's going to make this really easy is if we start at the origin, and there's actually 2 different easy ways to place this. This is one 3 by 5 unit rectangle. It would be 5 units across and 3 units up. And then you could also have a 3 by 5 unit rectangle going this direction. But notice both ways, I've started at the origin, so I can just count 1, 2, 3, 4, 5, and then 1, 2, 3. It's going to be really easy to find the lengths of the sides. The next example says a right triangle has legs of 6 and 8. Place the triangle in a coordinate plane, label the vertices, and find the length of the hypotenuse. In this case, putting a right triangle that has legs of 6 and 8, there's going to be, you could place it wherever you want to place it. However, again, if we start in the origin and we place it here, you could also place it with the 8 up on the y-axis and only 6 units on the x-axis. But this way, they're going to be pretty easy. The vertices ordered pairs are going to be pretty easy to plug into the distance formula because you're going to have one that is 0. So if you notice this coordinate, this ordered pair would be at 0, 6, and this vertex would be at 8, 0. So when I plug it in to the distance formula, it would be the square root of 8 minus 0 squared plus this plus 0 minus 6 squared. Well, 8 minus 0 is 8 squared, plus 0 minus 6 is a negative 6 squared, though. So it would be the square root of 8 squared plus a negative 6 squared. Well, 8 squared is 64, and negative 6 squared is a positive 36. When we add these two together, you get the square root of 100, which equals 10. Notice because the x or the y value in each of my ordered pairs was 0, my subtraction was really easy. It wasn't really that difficult of a distance formula problem. Now, regardless of where you placed this, you should, if you place it correctly and you label the vertices correctly, you should get the hypotenuse has a length of 10. However, these are just going to be the easiest ordered pairs to use. This next example says to find the coordinates of P. If you notice, if you're not paying attention, you could just think, oh, it's 6, 4, let's move on, we got it. However, if you notice the coordinates that they do give us, point O is at the origin 0, 0. Point N is at the ordered pair H, 0, and point M is at the point 0, K. To get to point P, so we don't really know if each one of the squares stands for 1 unit. We're not really sure what it stands for. But we do know that 6 units across is, for the x-axis, is H. And we do know that 4 units up on the y-axis is K. If you look to go to point P, to name the coordinates of point P, on the x-axis, we would have to move over like we were moving to point N, which has an x value of H, which means the p value, for the x value for point P is also going to be H because it is right on top of point N. And it's going to be the same thing for K because point M has a y value of K on the y-axis. Point P is right across from that point. You haven't moved any up or down, so it would be at K for the y value. So the ordered pair for point P, or the coordinate for point P, would be at HK. This next example says, in the diagram, triangle ABO is congruent to triangle CBO. Find the coordinates of point B. If you notice, we are given that the two triangles are congruent. Remember that if two triangles are congruent, their corresponding parts of congruent triangles are congruent. We're trying to find the coordinates of B, which, if you notice, is in the middle of the segment AC. If you look at the two triangles that were given, point AB, or segment AB, is going to be congruent to segment CB, which means that B is the midpoint of the segment AC. Because B is the midpoint, you're going to love this, you can use the midpoint formula to find the coordinates of point D. So this is using knowledge that we have previously learned. If you remember the midpoint formula, you add your two x values and divide by 2 to find the x value for your midpoint. And then you add the two y values of your endpoints and divide by 2 to find the value of your y value for your midpoint. When you do 0 plus 10 divided by 2, you get 5. And when you did 10 plus 0 divided by 2, you get 5. So that one wasn't too bad. The ordered pair for point B would be at 5, 5. The next example asks us to prove that triangle OPQ is congruent to triangle QRO. And notice that they've given us the lovely ordered pairs of O is at 0, 0, but then R is at HK, and Q is at H, and then K plus N, and then P is at 0, N. They have given us one nice thing, that it's sharing the side OQ, so that should be an easy one. We really don't have any way, especially because we are just given numbers, or we aren't given numbers, we're given variables. We really don't have a way to prove anything about the triangle, or about the angles of the triangle, so we're kind of out of luck there. However, it is in the coordinate plane, so we will be able to use the distance formula. And this is going to be a little bit tricky, considering we're using variables instead of numbers to plug into the distance formula. So we're going to start with PQ. To find the length of PQ, we would have 0 minus h squared plus n minus k plus n, and then squared. If you notice, n minus k plus n, my n's are going to cancel out. N minus n is going to be 0. So you are just left with the square root of h squared plus k squared. Because we're adding those two, we cannot pull out like an h and a k. If we were multiplying them together, then we could, but remember, when you're adding those two, we're not going to be able to just pull out an h or a k, even though they're squared. Next, let's find the length of PO. If you notice, PO, first of all, if you wanted to, you could not use the distance formula, but since we're using the distance formula, let's just go with it. When you do it, you get n. For OR, we're going to plug in 0 minus h and then squared plus 0 minus k squared. Well, negative h squared is h squared plus k squared. So notice that PQ and OR are congruent. And then to find the last segment that we need to find, which is QR, we're going to plug in what we know, h minus h squared, and then the square, and then in parentheses, k minus k plus n squared. My k's are going to cancel out in this case, so I'm going to be left with just, and my h's cancel out, so I'm just left with the square root of n squared, which is n. Like I said before, we can say that OQ is congruent to OQ because of the reflexive property. So because of the side congruence postulate, we can say that OPQ is congruent to QRO. Today's assignment is on page 246. It's numbers 6 through 19 all.